Let's get started with the concept of mole and molar mass. So the mole is a very popular idea and concept in chemistry. If you've taken chemistry, I am sure you've heard of it. The ACS has a little mole mascot that they use in some of their materials. So why do chemists always talk about moles? And that's because chemists work with things that are really, really small, and it's hard to count them. In fact, it's impossible to count them. I have an example here about counting something by weighing it. I used this problem with nails, so that is a good practice for a conversion problem if you want to take a look at the answer key to check that out. I think today I'm going to use a different example. I was inspired to find a better example, or maybe I was hungry, but I came up with this comparison of grains of rice. So grains of rice are really small. So when you have some rice, the number of grains you have is really large. So that's a little bit like atoms or molecules. They're so small that when you have a sample, the number of atoms or molecules you have is really large. So that makes it not convenient to talk about that number because it's so large. So if you were buying some rice, you wouldn't want to say, look, I'd like 42,000 grains of rice, because nobody's going to count out 42,000 grains of rice for you. The recipe would not be very convenient if it said that you needed 16,200 grains of rice for your recipe. So that's not very convenient either. So when you're buying something, you usually buy it in pounds or ounces. And when you're cooking, you use cups, because that's just a lot more convenient. You can do calculations if you know how many grains of rice are in a certain mass. So I took a little sample here. I've counted about 490 grains of rice in a 10-gram sample of rice. And so if we wanted to take a look at what each grain of rice is, and we know that it's $4.79 or 479 cents for a 2.27 kilogram bag of rice, then you can do some conversions on that, convert it to cents per gram, and then use this conversion factor. The 10 grams of rice are 490 grain, and you can get the price per grain of rice is about 0.0043 cents. So that is cents. In dollars, it would be $0.000043 per grain of rice. So, it's interesting, but that's not very convenient. You can't really pay for something with $0.000043, and you wouldn't want just one grain of rice, or even a dozen, or 100. So we use other quantities to talk about that. One thing that's a limitation I thought of for this comparison is that atoms and molecules are more uniform than grains of rice. So if you have a different kind of rice, short grain versus long grain versus wild rice, you might not get this same conversion factor. If you were to try it, you might be a little bit different. Whereas atoms and molecules are more uniform. Also, your recipes with rice don't really depend so much on the ratio. You don't need to have a recipe that's exactly, 32 grains of rice per bean. If you're making a recipe of beans and rice, it doesn't really matter, but reactions tend to have a more fixed ratio of elements and molecules that are reacting. So it does help to know how many molecules or how many atoms you're talking about, even though you can't really measure it that way. So that's where the concept of the mole helps out a lot. So atoms are so small that counting individually, or even counting as a dozen like this nail problem, is not very realistic. And so we can count things in moles instead of dozens. And a mole is just a number. So like a dozen is just the number 12 items. A mole is 6.022 times 10 to the 23rd power items. So that is a lot. Sometimes you can see a little cartoon or some kind of comparison that said if you had a mole of marshmallows, it would cover the whole entire planet Earth 6 feet deep. It's just a super mind-bogglingly large number. All right, so let's see if we can use it in a conversion. All right, this first one we're going to try to convert 0.873 moles of water molecules into individual water molecules. The relationship that we're going to use here is Avogadro's number. 1 mole of anything is 6.022 times 10 to the 23rd of that thing. Remember, a mole of items is this number of items. So this is our relationship. Starting with moles, we're going to write this relationship as a conversion factor with moles on the bottom to cancel out the moles. So we will take that 0.873, multiply it by Avogadro's number. Moles of water will cancel, and we will be left with water molecules. So we end up with 5.26 times 10 to the 23rd water molecules. So that is way more than you could ever count. You won't be able to check your answer there, but this is what the answer would be. So let's try a relationship here. We have moles of sulfur atoms and individual sulfur atoms. So this is our relationship. 1 mole of sulfur is 6.022 times 10 to the 23rd individual sulfur. All right, I set the problem up like this. We're starting with 4.73 times 10 to the 21st individual sulfur atoms. So this time we want the sulfur atoms and Avogadro's number on the bottom, and a mole of sulfur will be on top. We come out with an answer that's less than a mole of sulfur, because if you think about it, we have less than 6.022 times 10 to the 23rd sulfur atoms. 10 to the 21 is less than 10 to the 23rd. So we have less than a mole of sulfur atoms, and it's not too surprising to come up with a number less than 1. If you came up with a number more than 1, then you might be using multiplying instead of using the EE button on your calculator. So be careful with that, using scientific notation on your calculator. If you don't use scientific notation, then you should at least use parentheses to keep this 10 to the 23rd in the denominator. If you multiply, your calculator will move it up to the numerator. I noticed that I am using the abbreviation for mole, which is just MOL. So it's not that I'm forgetting the E, this is the official abbreviation. The abbreviation M is already taken, it means meter. The abbreviation capital M means mega. Small m also means milli. So M's are pretty much taken. So if you want to abbreviate mole, the only thing you can do is leave off the E. So why do we use this 6.022 times 10 to the 23rd as our number, Avogadro's number? So AMUs are really tiny. You can't really measure them very well, but what we can measure in the lab is grams. And if we have a mole of these AMUs, then we have a gram, which we can measure in the lab more easily. Okay, let's try calculating the formula mass and the molar mass of each of these compounds. So the formula chromium 3 oxide has 2 chromium and 3 oxygen in the formula. So we have 2 chromium and we have 3 oxygen. If you look on the periodic table, chromium weighs 52.00 AMUs and oxygen weighs 16.00 AMUs. These particular elements happen to be very close to whole numbers with their average atomic masses. Okay, so if we have 2 chromium and each chromium is 52 AMU, then our total mass of chromium is 104 AMU, and then our total mass of oxygen, 3 times 16 AMUs, we get 48 AMUs. And then we can add this up, and we have 152 AMUs. So I used multiplication here. You can use adding as well. If you add, the periodic table that I gave you goes 2 places past the decimal. So if you use that periodic table with 2 places past the decimal, then you can keep 2 places past the decimal. For this particular one, 3 times 16.00, you could keep 4 significant digits, so you can have 48.00 with multiplication. With this 2 times 52, it looks like I have too many significant digits because I have a 4 significant digit going to a 5 significant digit. But if you did this with adding, you could keep 2 past the decimal. So with our formula masses, if you're using the periodic table that goes 2 past the decimal, you're pretty much adding everything up. You can keep 2 past the decimal. So 1 unit of 2 chromium atoms and 3 oxygen atoms weighs 152.00 AMU. That is still amazingly small, even though 152 might sound like a lot. AMUs are just really tiny. So that is the formula mass. And then the molar mass would be how much does a mole weigh. So if we had a mole of chromium 3 oxide, then a mole of chromium 3 oxide would weigh 152.00 grams. So we can write the same number, 152.00, and instead of writing AMUs, we can write grams per mole of Cr2O3. So every mole of Cr2O3 is 152.00 grams. Every unit, I don't want to call it a molecule because it's ionic, but every piece of 2 chromium atoms and 3 oxygen atoms weighs 152 AMU. So our formula mass here is 152.00 AMU for just 1 unit of this formula. And our molar mass is 152.00 grams for every mole of the compound. So the molar mass, I think it's important to keep the units grams per mole. Some references will just report the molar mass in grams, and you're supposed to remember that that is grams for each mole, but I think that students tend to forget that if they don't actually use grams per mole as the units. So I would encourage you to use grams per mole for the molar mass. Alright, so let's have you try these 2 more during this video, and then the other ones I think I will leave for just the answer key for you to check your answers there. Alright, here we have PCl5. We have 1 phosphorus. Phosphorus is 30.97 AMU, so we have 30.97 AMU. We have 5 chlorine. Chlorine is 35.45. If you add up 5 of them, you can keep 2 past the decimal. So instead of just multiplying, we'll just act like we're adding it for the sake of significant digits, going 2 past the decimal. And then when we add these 2 numbers, it's kind of more clear to see that we can keep 2 past the decimal. So 208.22 AMUs for 1 molecule of PCl5. This one's covalent, so we can call it a molecule. And 208.22 grams for a mole of PCl5. Alright, for this last one, we have 6 carbons. Carbon is 12.01 AMU. We have 12 hydrogens. Since hydrogen is so small, I went ahead and put 3 past the decimal in the periodic table for hydrogen. So if you want to use 1.008, you can. If you want to just use 1.01, that's okay also. And then 6 oxygens is 6 times 16 AMU. So if we use 3 past the decimal for hydrogen, we can actually have 3 past the decimal here, but then that does go away when you add it to these 2 that go 2 past the decimal. So just remember that the molar masses and the formula masses calculated using the periodic table that we have will just go 2 past the decimal for the result. And this gives a molar mass of 180.16 grams per mole. The molar mass is the relationship between grams and moles of a certain molecule or atom. And so you can use the molar mass to do a conversion. Whenever you have a relationship, you can do a conversion with it. Iron on the periodic table is 55.85 AMUs, the average atomic mass. And so the molar mass of iron is 55.85 grams per mole. So if you have 1 mole of iron atoms, you would have 55.85 grams of iron atoms. In this particular problem, we don't have that much. We have a little bit less than a mole of iron atoms. Let's see how many moles we have. So here is our molar mass being used as a conversion factor. We have grams on the bottom because we want to cancel the grams and we want to talk about moles. And that ends up being 0.6204 moles of iron. And that answer makes sense. We can see that it's less than 1 mole. 1 mole would be 55. So looking at copper on the periodic table, the average atomic mass of a copper atom is 63.55 AMUs. So a mole of copper is 63.55 grams, because the molar mass of copper is 63.55 grams per mole. This time we want to have moles on the bottom to cancel, and we have grams on top. And this comes out to be 80.7 grams of copper. And that makes sense as well, because 1 mole is 63.55 grams. We have a little bit more than 1 mole. We have 1.27 moles, so it's going to be just a bit more than 63.55 grams. It's not going to be double this, but just a little bit more. So let's go ahead and take a look at these next problems. We're putting together Avogadro's number, individual silver atoms, and gram to mole conversions. So here is one relationship we know about silver. On the periodic table, we know that 107.87 grams of silver are in a mole of silver. And we also know that 1 mole of silver is Avogadro's number of atoms of silver. So starting with the individual number of silver atoms, we can see that we have more than a mole here. A mole is 6.022 times 10 to the 23. We have 10 to the 25, so a bit more than a mole here. So using this relationship over here, that a mole of silver is Avogadro's number of silver atoms, we're going to go ahead and put Avogadro's number on the bottom, because we want to cancel out silver atoms and talk about moles of silver. After this step, we would have moles of silver. We want to have grams, so we'll go ahead and use the molar mass. And we're going to write the molar mass with moles on the bottom. So now that silver atoms will cancel and the moles of silver will cancel, and we'll just be left with grams of silver. That's what we want. And it comes out to be 5,120 grams of silver. Let's try something similar with zinc. So on the periodic table, we can see zinc is 65.39 grams per mole. So 65.39 grams of zinc is 1 mole of zinc. And 1 mole of zinc is equal to Avogadro's number of zinc. Starting with grams of zinc, this is our relationship that has grams of zinc. We can convert it to moles. To do that, we put grams of zinc on the bottom, so grams will cancel. Now we would have moles of zinc. We want to cancel that and get individual zinc atoms. So now doing this, we'll cancel grams and cancel moles. We will end up with individual zinc atoms, and it ends up being 3.18 times 10 to the 21 zinc atoms. We can do a similar thing with compounds. We just need the molar mass. If we add 2 hydrogens and 1 oxygen, we see that water is 18.02 AMUs for 1 molecule, or 18.02 grams per mole. So this is our relationship. We want to write that relationship with grams on the bottom so that grams cancels. And so 500 grams of water is 27.75 moles of water. Carbon dioxide is 44.01 grams per mole. I got that from adding 1 carbon and 2 oxygen molar masses. And so this is the relationship. So we'll use the conversion factor like this so that the moles will cancel and we'll end up with grams. My calculator had given me 190.1232. Since I only have 3 significant digits here, I rounded it to the ones place, and I put a decimal just to show that it's 3 significant digits, not just 2. Let's go ahead and look at these problems where we can figure out the relationship between moles of a certain atom and moles of a compound. So when you're calculating the molar mass of aluminum nitrate, you add up that aluminum nitrate has 1 aluminum, 3 nitrogen, and 9 oxygen. So since 1 unit of aluminum nitrate has 3 nitrogen in it, then that means that 1 mole of aluminum nitrate would have 3 moles of nitrogen in it. So 1 unit of aluminum nitrate has 3 nitrogen atoms. 1 mole of aluminum nitrate has 3 moles of nitrogen, and 1 mole of aluminum and 9 moles of oxygen. But this is the relationship between aluminum nitrate and nitrogen. Then we can use this relationship as a conversion factor. We want moles of aluminum nitrate on the bottom so that we can cancel, and we will be talking about moles of nitrogen instead, and that comes out to be 2.28 moles of nitrogen. So going the other way, what if we had 2.56 moles of carbon atoms, and we want to know how many moles of glucose would be made from that or would contain that? So 1 mole of C6H12O6 has 6 moles of carbon in it, because 1 molecule of C6H12O6 has 6 carbon atoms in it. That's what you would do. You would add 6 of the mass of carbon when you're getting the molar mass of that compound. So this is our relationship between carbon and glucose. We'll write that relationship as a conversion factor with the carbon in the denominator, the C6H12O6 on top, and it comes out to be 0.427 moles of C6H12O6. You need several carbon to build this molecule. So when you build it, you're not going to get as many moles of it as you had carbon atoms. So it makes sense that it's smaller. Let's see if we can combine the relationships that we have here. We want grams of nitrogen and moles of aluminum nitrate. In this previous problem, we found out the relationship between moles of nitrogen and moles of aluminum nitrate. So we can use that to convert between moles of nitrogen and moles of aluminum nitrate. Now we need to factor in grams of nitrogen. If we look on the periodic table, we can see that the molar mass of nitrogen is 14.01 grams per mole. So we have 14.01 grams of nitrogen in 1 mole of nitrogen. So I think between this relationship and this relationship, we should be able to do this conversion. So this top relationship here, I wrote as a conversion factor with moles of aluminum nitrate on the bottom, moles of nitrogen on top, and then the next conversion factor has moles of nitrogen on the bottom and grams of nitrogen on top. So then this cancels, and this cancels, and we're left with grams of nitrogen, which is what the question asks for. And it ends up being 31.9 grams of nitrogen. Alright, let's try these last two in the section. Magnesium chloride, if you add 2 chlorine and 1 magnesium, you get 95.21 grams per mole as the molar mass. Let's write that as a relationship. Now we need the relationship between chlorine and magnesium chloride. So 1 mole of magnesium chloride, we just figured this out when we got the molar mass. There are 2 chlorine atoms in every unit of magnesium chloride, so there's 2 moles of chlorine in every mole of magnesium chloride. So that is the relationship between magnesium chloride and chlorine. Now we need the molar mass of chlorine. So starting with grams of magnesium chloride, we have that here in this relationship. We can use it to convert to moles. So now we would have moles of magnesium chloride. We can use this relationship to stop talking about magnesium chloride and start talking about chlorine, because that's what we're being asked about. So let's go ahead and put the magnesium chloride in the bottom. And then we'll have chlorine atoms on top, moles of chlorine atoms. And then every mole of chlorine atom weighs 35.45 grams. So if we do all of these conversion factors, we will cancel grams of magnesium chloride, cancel moles of magnesium chloride, cancel moles of chlorine, and we will end up with grams of chlorine. And that ends up being 39.35 grams of chlorine. So if we have figured out that there are 39.35 grams of chlorine in every 52.84 grams of magnesium chloride, we can use that to figure out the percent by mass. So out of the 52.84 grams of magnesium chloride, we just figured out that 39.35 grams of that mass is chlorine atoms. So if you had a certain total thing, like total people in the class, and you wanted to know what percent had completed an assignment, you would take the number that completed the assignment, divide it by the number in the whole class, and then multiply it by 100 to be able to express that as a percent, and that's how you would calculate the percent. Whatever special thing you want to look at over the whole thing, that will be a fraction, then multiply it by 100 to get a percent. And so in magnesium chloride, by mass, 74.47% of the mass is chlorine.